studying the first two quantum numbers, that is the principal quantum number and the azimuthal quantum number. Let us proceed towards the third quantum number, that is the magnetic quantum number, and see what is the significance of this quantum number. Magnetic quantum number is designated by the variable ml, m subscript L. What is the significance of this? Let us study. It tells us about the number of orbitals present in a subshell. See, we discussed earlier in our previous video lecture that each subshell is comprising of orbitals. For example, S subshell has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. So, this information about the number of orbitals present in a subshell is rendered by the third quantum number, which we call it as magnetic quantum number. So, it tells us about the number of orbitals present in a subshell by the formula 2L plus 1, where L is azimuthal quantum number. For example, if L is 0, that means we are talking of the S subshell, and we all know that S subshell contains 1 orbital. So, let us substitute L equals to 0 here in this, and we will get the value 1. That means there is 1 orbital present in the S subshell. In the same manner, for L equals to 1, let us see how many orbitals are there in the P subshell. So, substitute L equals to 1, 2 times 1 plus 1, that is 3, and we know that 3 orbitals are present in the P subshell. Let us take L equals to 2 corresponding to the D subshell. So, if we substitute L equals to 2, 2 times 2 is 4 plus 1, 5, and altogether we know that the D subshell comprises of 5 orbitals. So, by the formula 2L plus 1, we get to know the number of orbitals present in a given subshell. So, this quantum number, magnetic quantum number, gives an idea about the number of orbitals present in a given subshell. Number 2, it tells us about the orientation of the orbitals in the subshell. Orientation means how these orbitals are aligned along different axes. This information is also given by the magnetic quantum number. How? Let us see. S subshell, which is spherical in shape, has only one type of orientation. P subshell, which is dumbbell in shape, has 3 different types of orientation. One along the x-axis, another along the y-axis, and third along the z-axis. That is Px, Py, Pz. These are the 3 different orientation of the 3 orbitals belonging to the P subshell. Let us see what are the 5 different orientations of the 5 orbitals belonging to the D subshell. So, for D subshell, which has a double shape, the 5 orientations are: one is dxy, another is dyz, third is dxz, fourth is dx square minus y square, and fifth is dz square. If you talk of first 3, that is dxy, dyz, and dxz, remember that the lobes of the double dumbbell in these 3 orbitals are lying between the axes. That means if you talk of dxy, this is x-axis, this is y-axis. So the lobes of the double dumbbell, they are lying between the axes. In the same manner, dyz, this is y-axis, z-axis, lobes lying between the axes. In the same manner, dxz, this is x-axis, this is z-axis, lobes lying between the axes. But if you talk of the next d orbital, which is dx square minus y square, here the lobes are lying along the axis. And even the last one, dz square, which has a shape of donut, here also the lobe is lying along the axis. So remember, for these 2 d orbitals, dx square minus y square and dz square, if you see their orientations, you will find that their lobes are lying along the axis. But for these 3 d orbitals, dxy, dyz, and dxz, their lobes are lying between the axes. So these are the 5 different orientations of the 5 d orbitals belonging to the D subshell, and this information of the orientation is provided to us by the magnetic quantum number. For any L value, the value of magnetic quantum number will be ranging from minus L to 0 to plus L. What does this mean? That, for example, if L is 0, then minus 0 plus 0 doesn't have any meaning. So M value will always be 0. For L0, M will be 0. This shows that for the S subshell, we have only one type of orientation which is possible since the shape of this subshell is spherical or circular. If you talk of L equals to 1, that is the P subshell, then the values of magnetic quantum number will be minus 1, 0 and plus 1. These three values are indicating the three different orientations of the three orbitals belonging to the P subshell, that is Pxy, Py, Px, Py and Pz. In the same manner, if you take L equals to 2, there will be 5 possible M values. That means minus 2, minus 1, 0, plus 1, plus 2, indicating that all 5 d orbitals of the d subshell have 5 different types of orientations. Now, so this was the significance of magnetic quantum number. Now, let us see the last type of quantum number, which is the spin quantum number, designated by M subscript S. It tells us about the spin of an electron, whether moving in clockwise or anti-clockwise direction around the nucleus. See, whenever the electron is moving around the nucleus, it is not only moving around the nucleus in circular path, it is also spinning on its own axis. So, this spin of electron may either be in the clockwise direction or maybe in the anti-clockwise direction, and this information about the spin of electron is provided by the last quantum number, which we call it as spin quantum number, which may have only two possible values, plus half or minus half. So let us see, if S is plus half, then this indicates that the electron is spinning in clockwise direction and it will be like this in upward direction in an orbital. If S is minus half, the electron will be spinning in the anti-clockwise direction and it will be placed like this, downward spin in the orbital. So, for example, you all know that an orbital can contain a maximum of 2 electrons. So, both will be in opposite spin. That means this one spinning in clockwise direction will have S value of plus half, and this one spinning in anti-clockwise direction will have a S value of minus half. So, the spin of electron is indicated by the last quantum number, which is the spin quantum number. So, this is all about the quantum numbers, and let us proceed towards the concluding topic of the chapter, that is rules for filling of electrons. So, let us see number 1 rule. Before that, let us do one question related to quantum numbers. Calculate the values of all 4 quantum numbers for the valence electron of sodium. In all such type of questions, you will be first required to write the electronic configuration of the given element. And we have already learned in our previous video lecture, Structure of Atom Part 1, we have already learned how to write the electronic configuration of elements. So for sodium, how will we write? Neon 3s1. So this is the valence electron. If the electron is in 3s, N value will be 3. For S, L value will be 0. If L is 0, M will also be 0. And since this electron is in the upward spin, therefore S value will be plus half. This is how we predict all 4 quantum numbers for any given electron in an atom of an element. And now we proceed to the last topic, and that is rules for filling of electrons. The very first rule we had already studied in our previous video lecture. You have to see that lecture so that, because many things are interconnected with the electronic configuration, especially this quantum number portion. So you need to go through that video lecture thoroughly and learn how to write the electronic configuration of elements. And there we studied, if you remember, the off-Bohr principle. Off-Bohr principle is the major or the important principle which we follow while writing the electronic configuration of the elements, and this states that electrons are filled in the subshells in the increasing order of their energies. Electrons are filled in the subshell in increasing order of their energy means that the subshell with the lowest energy will be filled first, subsequently filling of these subshells in the increasing order of their energies. So it states that Ampere principle states that electrons are filled in the subshells in the increasing order of their energies. The second rule is the N plus L rule, also known as Bohrs-Bury rule. N plus L rule, also known as Bohrs-Bury rule, states that if for a subshell the N plus L value is lower, that means it will have lower energy and it will be filled first with electrons. So it states that subshell with lower N plus L value will have lower energy and will be filled first with electrons. For example, let us take 4s in 3D. Let us take the case of 4s in 3D. We know according to the diagram of the Ampere principle that 4s is filled prior to the filling of 3D. Why so? Let us explain it according to the Bohrs-Bury rule. For 4s, n is 4, L is 0, because for s subshell L is always 0. So n plus L comes out to be 4. But for 3D, n is 3, L is 2, n plus L comes out to be 5. That means for 4s subshell, the n plus L value is lower. That means 4s will be of less energy than 3D and hence will be filled first with electrons. Let us see another case. What if the two subshells have the same n plus L value? For example, 2p and 3s. Let's calculate their n plus L value. N2, L1, n plus L3. In the same manner, for 3s, N3, L0, n plus L3. That means both of them are having same n plus L value. Then in that case, we have to refer to the n value. Lower the n value, lower will be the energy. We had already discussed this in the significance of principal quantum number, that n value is directly proportional to the energy of electron. So lower the n value, which is lower for 2p, therefore 2p is of lower energy than 3s and will be filled first with electrons. So this is what is meant by N plus L rule or Bohrs-Bury rule. Next rule is the Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity, it states that in a set of degenerate orbitals. What do we mean by degenerate orbitals? Orbitals of same energy. Like these three are the degenerate orbitals, orbitals of same energy. When we are filling the electrons in a set of degenerate orbitals, first we have to singly fill electrons in them and thereafter the pairing will take place. So it states that pairing of electron in degenerate orbitals will only occur when all the electrons are when all the orbitals are singly occupied with electrons. Let us take the case of nitrogen here. Configuration is 1s2, 2s2, 2p3. 1s will contain two electrons. 2s orbital will contain again 2 electrons. But 2p, while we have to fill the 3 electrons, we have to first fill 1 in each of the degenerate p orbital. Thereafter the pairing will occur. But since it is having 3, so 1, 1, 1. It will not be like this. It will violate the Hund's rule of maximum multiplicity. So this is what is Hund's rule, which states that while filling the electrons in degenerate orbitals, first we have to singly fill them with electrons and thereafter the pairing would occur. So this is the Hund's rule. And next we will study about the Pauli's exclusion. Let's now learn the last rule for the filling of electrons, and that is the Pauli's exclusion principle. Pauli's exclusion principle states that no two electrons in an atom of an element can have all 4 quantum numbers same. That means for any 2 electrons in an atom of an element, all the values of all 4 quantum numbers will never be same. Or alternatively, it also states that an orbital will accommodate a maximum of 2 electrons, and that too in opposite or anti-parallel spin. What does this mean? Let us take an example of the element helium and learn that how no 2 electrons in an atom can have all 4 quantum numbers same. So taking this example of helium, let us write the electronic configuration. It has the configuration of 1s2, If I distribute these two electrons in the orbital, they will be like this. So for the first electron, which is present in 1s, n is 1, l is 0, m is 0, and s is plus half since it is having a clockwise spin. For the second electron, n is 1, l is 0, m is 0, but s is minus half. That means it is very clear from this example that these two electrons are having the value of spin quantum number, that is the fourth quantum number, different. That means even if the three values are same, the fourth one will be different. That means we can say that no two electrons in an atom can have all four quantum number values same. Then let us talk of this another alternative statement. It states that the orbital can accommodate a maximum of 2 electrons, and that too in opposite or anti-parallel spin. Had the electrons been present in parallel spin, the values of the fourth quantum number for both the electrons would also have been same. Both would have a value of spin quantum number equal to plus half. That means it is not possible according to Pauli, and hence we say that an orbital will accommodate 2 electrons, and that too in opposite or anti-parallel spin. Only when they are in anti-parallel or opposite spin, the values of spin quantum number for these two electrons will never be same. Let us take another example of lithium configuration 1s2, 2s1. If you draw the orbital diagram, 1s will contain 2 electrons in opposite spin and 2s will have 1 electron. So let this be the first electron, this one be the second, and this one be the third. So for all these 3 electrons separately, let us predict the values of all 4 quantum numbers. So for the first electron, n value is 1, l value is 0, m value is also 0, and s is plus half. Let us talk of the second electron, where n value is 1, l is 0, m is 0, all 3 values are same. But this fourth one is different because the electron is in opposite spin, that is the anti-clockwise spin. Let us talk of third electron, that is n is 2 because it is present in the 2s subshell. So n is 2, l is 0, m is 0, and s is plus half. So if you compare the first and the third electron, you will find that the n value is different. If you compare the second and the third electron, you will find not only n value but the s value is also different. That means no two electrons in an atom can have all 4 quantum numbers same as stated by Pauli, and the principle is called Pauli's exclusion principle. So these were the various rules to which govern the filling of electrons in the atom of an element. Now let us practice a few questions from your NCERT back exercise related to the quantum numbers. So let us take this question, question 2.25 from your NCERT back exercise, and the question is, an electron is in one of the 3D orbitals. Predict the values of all 4 quantum numbers. If it is in 3D, n is 3, for D, L is 2. If L is 2, a magnetic quantum number may have either minus 2 value, minus 1, 0, plus 1, plus 2. Because we studied that for any L value, the value of M will range from minus L to 0 to plus L. So if L is 2, M will have 5 possible values, minus 2, minus 1, or 0, or plus 1, or plus 2. And S may have plus, minus half, any of the 2 values, either plus half or minus half. So this is how we predict the values of all 4 quantum numbers for any given electron present in any subshell. Now, let us see, describe the orbitals. 2.29 question, describe the orbitals. N1, L0. That means we are talking of 1s subshell. If n is 3, L is 1, we are talking of L is 3, L is 1, we are talking of the 3p subshell. If n is 2, n is 4, L is 2, we are talking of the 4d subshell. If n is 4, L is 3, we are talking of the 4f subshell. Or else you may be given like this, for example 3d subshell. You may be asked to predict the values of n and l. So for 3d, n is 3 and L is 2. So this is how this information basically will tell you about the type of subshell in which the electron is present. Now question number 2.30, which of the following sets of quantum numbers are not possible? Let us see. Number 1 set. Let us look at the values of all four quantum numbers and see which one of the value is wrongly given or it is not possible. Here n equals to 0 is not possible, so this set of quantum number is wrong since n can never be equal to 0. The second n1, L0, ML0, MS minus half is absolutely correct because all the values are in accordance. Next is N1, L1 is not possible, this is wrong. So this is wrong since n can never be equal to L. The next one, N2, L1, ML0, MS plus half is absolutely correct. The next one again, N3, L3, again the same thing, that is n can never be equal to L. And the last one, N3, L1, ML0, MS plus half is also absolutely correct. So, if the sets of quantum numbers are given, we should be able to identify whether the given sets are correct or not, because we have already studied about the quantum numbers. So, we can easily predict whether the given set of quantum numbers are correct or not. Let us talk of question number 2.31. How many electrons in an atom can have the following quantum numbers? So, n equals to 4. n equals to 4, that means the n energy level, that is the n shell, and the number of electrons that can be accommodated in the shell is calculated by the formula 2n square. So, for n shell, the n value is 4. And 4 square is 16 and 16 into 2 is 32. Altogether 32 electrons will have the value of n equals to 4. But remember that out of 32, 16 will have the spin in plus half and 16 will have the anti-clockwise spin, that is minus half. So the answer is 16 because out of 32, half will be having spin in anti-clockwise direction with s value minus half. Remaining half will have the spin in clockwise direction with s value plus half. Let us see the last one. N equals to 3, N equals to 0. We are talking of 3s and 3s will have a maximum of 2 electrons because 3s subshell contains one orbital and one orbital will accommodate a maximum of 2 electrons. So this is the end of the unit structure of atom. It is the very important unit from competitive point of view also, and it is the base for the further units. So prepare this unit thoroughly, solve the NCERT questions given in the back exercise, and if you have any queries, please let me know in the comment section so that I can solve all your queries. Thanks for watching. Have a nice day.